So when I finished talking about likelihood ratios in the last lecture, one of the things that I said is that you can't really use likelihood ratios to compare models that have very different sets of parameters. So backing up a step, what that means is that when we're comparing models, there's really kind of two different kinds of model comparisons that take place. One is when we're comparing parameters that are different parameter options for basically the same equation. So you have the same basic process with different details. For example, if we have two lines with different slopes, or if we want to compare two group averages to see if those two groups are different from each other or not, those are competing parameters. And so you might consider it something like when we're looking at different kinds of apples, everything here is an apple, but it's just the details and how the apples differ. Alternatively, we might have different processes entirely where some of the parameters that you use to describe an apple aren't relevant when you describe a banana and vice versa. And so you might actually have totally different parameters in your different model equations. And so we can't directly use a likelihood ratio. We have to figure something else out in order to compare them. And so what we use for those oftentimes is something related to Occam's razor. So Occam's razor is the famous idea that simpler models are better than complex ones. And because what we're trying to do is kind of say one model or another is not good enough, you can think of a more complicated model as being something that contains a simpler model inside it, right? So if you've got 4 parameters for this complicated model and 3 parameters for this one, then maybe those 3 parameters are a subset of those 4 parameters. And so if they're otherwise equal, then why not use the simpler one? It's easier to test. We only have 3 things to test. It's just better. So we generally prefer or have think a model with fewer parameters is more plausible than one with more parameters. And so the term for a model that a quantity that takes the likelihood and penalizes the model's likelihood by some factor according to how many parameters are estimated is called an information criterion. And so Hirotugo Akaike came up with the Akaike information criterion in 1974. And the way that works is you take the log likelihood and you multiply it by -2. So then that's going to be so before a high log likelihood was good, so now we want a low Akaike information criterion. And then you add twice the number of parameters you've estimated to that. Again, so that's penalizing, so it's making it higher. And whatever thing has the lowest Akaike information criterion is going to be your best model. And this is a score that lets us compare different models, even if they have different numbers of parameters. A similar sort of thing is the Schwartz or Bayesian information criterion, which in addition to penalizing the model by the number of parameters it has, it also penalizes it by the sample size. So here we've extended the Akaike information criterion. Not only can we compare models with different numbers of parameters, but the Bayesian information criterion actually even lets us compare models that might be being tested with different data sets of different sample sizes. So that's really cool. So these are 2 different things where if you compute the information criterion for your model and then compare it to a competing model, whichever one has the lowest information criterion score is the one that you're going to choose. And I think that is the end of the information criterion. There might be one more. Yes. So in both cases of these information criteria, what we had is we had the likelihood, which is a measure of how good the model's fit was to the data, and then we weighted it by how reasonable the model was. And in both those information criteria quantities, the weighting was the more parameters your model has, the less plausible or less reasonable you think it is. So simpler is better. so you can generalize for that and say, okay, counting parameters is one way we could determine the plausibility, but it's not the only way. In fact, sort of the natural way of doing that we have is when we get new evidence to make a decision about something, we aren't comparing that evidence in a vacuum. We're thinking about it in terms of what is our previously formed opinion about that. So if we see a coin flipped 4 times and it comes up 3 heads and 1 tails, we might think that it's bent, but on the other hand, it's pretty hard to do that, and heads and tails, so it's a nice flat coin, that's pretty simple. And so probably we just by luck didn't get an exact 50-50 distribution, and so we might not immediately jump to the conclusion that it's an unfair coin. We might have some prior probability that we assign. So the next topic we're going to talk about incorporates that formally into the mathematics